Hello and welcome back. In today's video, we are going to start with a problem. Basically, we are going to start with here heat transfer module, heat transfer in solids module, and this will be our first video. And in this video, we are going to solve this problem, which is a one-dimensional heat conduction problem. And we are going to solve this problem in two ways. And in first way, we are going to solve it using pen. We are going to solve it analytically and using the formula that we study in our graduate course. And after that, we are going to solve the same problem using COMSOL Multiphysics. We are going to solve it numerically, and we are going to compare the two solutions. So the problem here is that a big copper spoon with a long cylindrical rod is kept in a vessel in which water is boiling. The diameter of the rod is 4 centimeter and its length is 100 centimeter. What is the average heat conduction rate through the handle? Find the temperature distribution along the axis of the handle and the temperature at the midpoint of its midsection. Assume one-dimensional heat flow. The problem is like this. We have a vessel in which water is boiling, and in this big vessel we have a spoon with a long handle, and its dimensions are given. Its length is given as 100 centimeters and its dia is given as 4 centimeter. And it is given that it is made of copper, so we know the material as well. And what we know is boiling water is usually at, when we talk about 1 atmosphere, it is at 100 degrees Celsius. So one end of the rod is at 100 degrees Celsius and another is exposed to air, say it is room temperature 20 degrees Celsius. So this is our problem that we are going to solve. What we are going to do now is we are going to solve it analytically first. So let us start. So analytical solution, what we have here is the assumption is that assume one-dimensional heat flow, and we know from Fourier law of heat conduction that when heat flows through a solid material, through something, it is governed by the Fourier's law in 3 dimension, but in one-dimensional flow, the equation reduces to second derivative of temperature is equal to 0. This is for one dimension steady state. So this is our condition. So we are not studying the temperature variation over time. It is constantly, one end is constantly at 100 and another end is constantly at 20 degrees Celsius. We are simply studying it using steady state condition. So we are left with this equation, and when we solve this equation for this temperature distribution, and we know this temperature distribution along the axis, if suppose this is a rod and it is kept along x-axis, the temperature variation along this axis is equal to the higher temperature side plus lower temperature minus higher temperature divided by length into x. So this is our equation. If we rewrite it properly, what we have here is we have a rod, and this is the x direction. So this temperature distribution, when this differential equation is solved for T of x, the solution we know is higher temperature plus lower temperature minus higher temperature divided by length into this x. So first of all, let us find this temperature distribution. So this temperature distribution is equal to higher temperature is 100 degrees Celsius, lower temperature side is 20 degrees Celsius, length is 100 centimeter, which means 1 meter, and this diameter is 4 centimeter, means 0.04 meters. So higher temperature in SI system will be 373.15 plus, then lower temperature will be, since it's the difference between the temperatures, so it's one and the same thing whether we use Kelvin or degree Celsius in here, but not here. And it's alone, we have to use Kelvin. But here in the difference, 273 will get cancelled out anyways, so it will be lower temperature 20 minus high temperature 100 into x divided by 1, which is equal to 373.15 plus this will be rather minus, plus minus, so 20 minus 100 will be minus 80 divided by 1 is 80 again, so minus 80x. So this is our temperature distribution along the axis of the rod. So we have found this. Now what we can see here is it's a variable something like y, it's a constant c, and this is something like m, and this is x. Y is equal to mx plus c. So this temperature distribution is clearly decreasing linearly because it is the equation of a straight line, y is equal to mx plus c, and this is the c part here, this intercept, which will be 373.15, which means it is intersecting at 100 degrees Celsius to this temperature's axis, and it will decrease to 20 degrees Celsius. Say here it is 20 degrees Celsius, it will decrease linearly because this comes out to be y is equal to mx plus c form. So this is the temperature distribution, and using this temperature distribution we can find the temperature at the mid section. This is the temperature along the along the rod at all sections. We can find it at the mid section, which is total length is 1 meter, so mid section will be 0.5 meter, so we can put x is equal to 0.5 here. So what we will be having is value of t at 0.5 meter will be 373.15 minus 80 times 0.5, which is 373.15 minus 80 into half is 40, so it will be 373.15 minus 40, so it will be 333.15 Kelvin, or which is, if we do minus 273.15, so it is 60 degrees. So at the mid section the temperature will be 60 degrees Celsius. So we found the temperature distribution, we found the temperature at the mid section. Now heat transfer rate. So if we find heat transfer rate, so we know for one dimension this heat transfer rate is K area temperature difference divided by this length of the heat along which the heat is being transferred. So Q dot will be a K. K is a material property, and it is saying that a big copper spoon, so it is material is copper in our case, and K for copper is 398 watt per meter Kelvin, around this. So 398 into area will be pi by 4 into d squared. Diameter is 0.04 in SI units squared, into temperature difference will be same 100 minus 20, and divided by length will be 1 meter in SI unit. So it will be 398 into if we solve this whole thing here, so it will be 398 into pi into 0.04 into 0.04 twice into 80 divided by 4, so it will be 40, around 40.01, so it will be something like 40.01 in SI units, which is watt. So this is so what we found here is our temperature distribution 373.15 minus 80x over mid temperature 60 degrees Celsius, and our heat transfer rate came out to be 40.01 watt. What we will do now is we will calculate the same three quantities using the numerical method. For that, we will open the COMSOL Multiphysics software. We will open Model Wizard. Now our rod, our spoon has a cylindrical rod which is three-dimensional. No doubt we are solving for one dimension, but the geometry we will be choosing three dimension. For physics, it is a heat transfer, heat conduction problem. So heat transfer in solids. We'll add this physics. Then about the study, we are just studying the stationary. We are not studying the temperature variation with the time. We just studying the temperature variation along the with position along the x positions. So stationary and done. We have added the physics component and the study along the way. Now what we will do is, first of all, unit is chosen as meter. We'll keep it. Then we'll go to geometry. We'll right click on the geometry. Either we right click on the geometry here, or we have geometry section here, and we can create geometry from here as well, or we can go to geometry section and see these tools like cube or cone or cylinder. We can use these elements to create the element to create our spoon. So we'll simple way is to right click, and since we need to create a cylinder, so we will click cylinder. Our radius is, our diameter is 4, so radius will be 2. Radius will be 2 centimeters, which means 0.02 meters, and our length, which is height of the cylinder here, it is 1 meter. It's 100 centimeters, which is 1 meter. And position we'll keep it along x-axis, and we will build our spoon's handle. Now we have to tell the COMSOL that it is made of copper. COMSOL now knows the geometry. Now it has to know what is the material. So we'll right click on the material. We'll add from library, and I will find the copper. I have added a copper material here with the same thermal conductivity and similar properties. So what we have to do here is I used value of K 398 there. So I have to choose copper may be having different, here library may be having copper, different versions of copper. We have to check whether the thermal conductivity is same or not. So I have created a copper with basic density this and thermal conductivity 398, which we used in the analytical method. So same property should match, then we can expect the comparison, perfect comparison. So I have added the material as well. After that, what we'll do is, after that we have added the physics. It is solid, initial value is 20. Let's keep it because it's room temperature. So right click the heat transfer. Then we have to add the, we have made the geometry, we have add the material. Now we have to add the boundary conditions of the physics. The heat transfer's boundary condition that we need here is temperature. We right click on the physics, we click temperature, and we set the temperature on this side. On one side is 100 degrees Celsius, which is 393, 100 degrees Celsius, which means 373, sorry, so 373.15 Kelvin on this side. And we will again right click temperature, and we will set this temperature as 20 degrees Celsius, which is 293.15 already set. We will select for this, we will select this end. So this end has been assigned 20 degrees Celsius, and this has been assigned 100 degrees Celsius. And rest this the curved surfaces have not been assigned with any boundary condition. So by default they will be overridden by this thermal insulation, because this is the default boundary condition. If we do not apply any boundary condition to any surface, or we forget, it gets automatically assigned to that surface. Since we are interested in one-dimensional heat transfer, so this heat will flow from this end to that end. and that's why we have insulated the surrounding surfaces. The next part comes is to discretize this geometry. That's called meshing here. We select the mesh, then we keep everything as it is, then we will build all, so it has meshed it, converted into small elements. Then we go to study. Under study there is a node called stationary that we have added. We selected this and its settings will open here. Then we will not change anything. For now we will keep everything same because we are solving basic problems, and the inbuilt settings are the best for these basic problems. So what we will do is we will run the simulation by clicking this compute. So we'll compute, we'll click it, and it will start solving for us. Now it has solved this problem for us. Now this is the color bar here. We can come to the settings window, show maximum and minimum values. We can check it, and we can see in the rod the maximum temperature somewhere is 373 and the minimum temperature is 293. We can check the show titles. We can check the units as well. So 373 Kelvin is maximum, 293 Kelvin is minimum, which is the 120 degrees Celsius that we already know on the two ends. So this is the temperature distribution in the form of color gradient. Now what we have to do is, first of all, we have to calculate the temperature distribution through the rod. So how we will calculate this temperature distribution is, we will go to results, we'll right click, we'll go to data set, the first option under the results, we'll right click. First of all, what we have to do is we have to plot the temperature along this rod. For that we will select a line along the axis of this rod. So first of all we have to draw a line that will act as the axis of this rod. That is why we'll go to data set, right click, and we will choose. What we have to do is we have a 3D object and we have to draw a 1D line through it. So when we have to draw something inside of this material, it's called cut. And if we do the thing that we are drawing, the element that we are drawing is line, so it's called a cut line. If it were drawing it through 3D object, it's called cut line 3D. So it's a 3D object, we are drawing a line through, so it's a cut line 3D. So cut line 3D, we will select it. So we have added cut line 3D. Now we have to tell this COMSOL where this line should be. It should be the axis of this rod. That means it should start from this end to that end. So this end is the origin. If we can see 0 0 0, so this is the origin. So 0 0 0 is set 0.1 and 0.2 will be on that side for this line segment. So which will be, so y and z will be same, but x will be changing from 0 to 1 meter. So x is set to 1 by default and y is kept as 0 and z is kept as 0 for the 0.2. So when we click plot, so that this red line has been plotted along the axis of this rod. Now we have to plot the temperature distribution along this line. Now we have told the COMSOL this is the line along which we want to calculate this temperature, we want to find this temperature distribution. Now what we have to do, we are done with the data set. Then all the data that it has derived while solving this problem is saved in derived values. Then we go to derived values. We first of all we have to draw the graph. So the for graphs we have to go to results and open the options, right click it. Then we have 3D plot, 2D plot or 1D plot. No, we have to draw just the 1D plot. We want to see how temperature varies along this axis. So it will be a line or a curve. So 1D plot, we click the 1D plot group. So it opens a graph. Nothing is there because we have to select. So a graph paper will appear and the settings window of it. What we have to do is we have to go to the settings window. Then there is this data set. In the data set we have already made the cut line 3D. So we will go to the data set in this settings and find that cut line 3D that we have made. So it will appear here. We will select it, cut line 3D. Now we have told this graph setting that the graph you have to draw along that line that we made. Then what we have to do is click plot. First of all we will go to for that we have to 1D plot groups, maybe of different types. 1D plot group it may be of several types. maybe a single graph, a line, or something else, maybe something like a spider curve or spolar curve. It may be of different types 1D plot. So we have to tell it which plot we want to draw, which is of course 1D, but which type. For that we have to right click this option and tell him which line we want to draw, which graph we want to draw, line graph, point graph, or histogram, what type of graph. So we'll click line graph here. Under this comes the line graph. Now, and it is settings. In the setting there is again data set. We'll click it and again select this cut line 3D. Then along y-axis, expression is along y-axis, that is capital T, temperature, and its unit is set Kelvin. Let us keep it degrees Celsius. Then we can give description as well. Description is by default given, it is the temperature graph. Then we will click plot. When we click plot, we have a straight line which starts from 100 degrees all the way to 20 degrees Celsius in the linear manner. This is what we got here. This is what we got from the previous page that we found here. Yeah, so we found this linear equation, and its graph was a straight line starting from 100 decreasing all the way to 20. So our simulation is confirming this. So first one we have compared that we have exactly getting the temperature distribution same as the analytical one, a straight line starting from 100 all the way to 20. This is the first part. The second part is to find the temperature at the midsection from this temperature distribution. So what we can do is, for that, what we have to do is midsection. We have to select a point in the midsection and then find the temperature at that point. First of all, we have to tell it. We have to assign a point, say in the same way as we have made a cut line 3D. So since it's a point, it's not a line, but still it's inside a 3D object, 3D geometry. So cut line, so it will be instead of a 3D cut line 3D, it will be cut point 3D. So again, data set, right click, cut plane, cut line, cut point. So ours is now cut point. We'll select it, its settings open. We can choose the coordinates of the point. So coordinates of the point will be, it's exactly at the center. That means y0 z0, but x is midpoint, which is 0.5. So x will be 0.5 and y0 z0 we will plot. So we have the point exactly at the center. At this point we want to calculate the temperature. So what we'll do is we will close this data set. We have made the point. Now we'll go to results, right click, again okay, we are not plotting anything. We have to calculate the value. That when we have to calculate, the calculation is done from derived values. We right click on the derived values. We have to evaluate something at a point. So point evaluation and settings will open. We will go to data set, same data set. It will contain our point, cut point. So we will find our cut point 3D, select it. Here we have temperature and unit Kelvin. We can change this unit from Kelvin to degrees Celsius, and for degrees Celsius small DEG and capital C is the code, is the degrees Celsius. Then what we'll do is we will click here evaluate. So it will evaluate for us, and we can see here the temperature in degrees Celsius at this 0.5 meter point is 60 degrees Celsius. If we go back and check, it was analytically 60 as well. Now we have to calculate the heat transfer rate. We'll go back. We have to calculate, means we have to evaluate heat transfer rate. So what we'll do is, again we go to derived values. We right click whenever we have to calculate something. So derived values. Now we have to calculate the average heat transfer rate. We'll go to average. Then heat transfer rate through what? Through this rod. We'll calculate average through this rod is 3D volume. So volume average we have to find. Steady is already selected. Here we can change unit, or need to change this unit because we are not calculating temperature, we are calculating heat rate. So by default, temperature will always be selected here in the heat transfer module. What we have to do is we have to go to this option, left click it, then we have to find this heat transfer in solid, that is this physics that we are using currently. We have to open it, then we have domain fluxes, open this domain flux. Then first one is convective heat flux we want to find, or conductive. Since a conduction, so conductive heat flux, we'll double click here. Now we have here the conductive heat flux, but we can see it is in terms of flux, watt per meter square, but we want to find it as a rate, which means over, not per meter square, but over the entire area. For that, what we'll do is we have to modify this expression. We have to multiply how can we convert flux into heat rate? We have to multiply it with area, because flux is per unit area. So how we multiply it with area is, whatever expression is there, we will put this asterisk, which is the multiplication operator here. So we have to multiply it with area. Area will be pi r square. So pi, for pi the code is pi into then radius r. What is r? Our radius is 0.02 meter here. So 0.02, this is the symbol for power, then 2 bracket close. So pi r square, and we have to assign the unit. For unit we know square bracket, I have told this, we have to start the square bracket, then unit for this area that we have added is meter square obviously. So meter, then again power 2, which is meter squared, close the square bracket, and we click outside. We can see we have multiplied the area, and the flux is now converted into heat rate, because watt per meter square has become watt, so it is the heat rate. So it is the heat rate, conduction heat rate, that we are finding. So what we will do is we will calculate here. We will click the evaluate, and okay, let me see. Okay, we have not selected it. So average over this, we have to select over this rod, then we'll calculate evaluate. Now we have heat rate of, okay, let us delete this column first, the previous column, because we did not select previously. We added this volume average operator. We told the COMSOL to calculate this average through this volume average operator, but we did not select it. We did not tell it for this object. So we selected it. So we clicked the evaluate, and it gave us heat rate of 40.011 watt. So if we compare it with this value, here we have 40.01 watt exactly 40.011 watt exactly, which means 100% accuracy, exact answer, no error at all for these basic problems. So this is how powerful COMSOL Multiphysics is, and this is what we can do with it. It's very powerful, and we can calculate this within a couple of minutes for these simple problems. As the problem gets complicated, it will take more and more time, but that which would otherwise take hours or days to solve this, using this COMSOL Multiphysics software, this numerical simulation software, it would take minutes or hours at most, depending upon the performance of your PC or computer. So this was all about the today's class. Next time we will start some another problem of different nature. Today we started with a cylindrical rod and studied a one-dimensional heat conduction. Next time we will change this problem to a different one and learn another concept through that, and learn how to solve that kind of problem in COMSOL Multiphysics. Thank you.